Okay, so here we are. We are going to be doing one more method for solids of revolution, and that's the shell method. So we've done disk method, washer method, and then our third one is shell method, and that's the last of the solids of revolutions. And then we will do cross sections on Thursday or Friday, depending on when I have your class. So if you haven't already, get out a piece of paper for notes, your graphing calculator, and that's it. Okay, so we have 6.3, which is shell method. And what we are doing is very much like what we've been doing, is we will be given a function, sometimes two, sometimes three functions, and we're going to spin it around the axis of revolution, and then depending upon our perspective as far as the y-axis, the x-axis, there's one method that's easier than the other. So you can interchangeably use shell method with disk or vice versa, and washer as well. So let's just draw a random function. So there's my random function. I'm going to call it f of x. And then we're going to go from a to b. Okay, so random function from a to b. And that is my bounded region to the x-axis. So I'm going to just kind of give it a little bit of a shade. And then this time we are going to spin it around the y-axis. So when we call it the shell method, what we do is we take the perspective of one rectangle, just like we do for disk or washer. And if I take this one rectangle and spin it around the y-axis, it creates the shell of a cylinder. So kind of like the candy coating on an M&M, this is the candy coating on a cylinder. That's a joke. So when I spin it, so I'm just going to reflect it across the y-axis. And then when I connect it, because it is spinning, it creates this little cylinder. And so that's the shell of a cylinder. And if I could imagine, I take one little rectangle off that entire shaded region and spin each one, then I have all of these cylinders that are slightly different in size and height, all nested together, and all of that nesting together creates my volume. And that's what we're doing. So in order to do that, we have to think about, okay, that's really the surface area of a cylinder, and what is that formula? So in the past, we did area of circles, pi r squared to do disk and washer method. So for us, our little geometry review is the surface area of a cylinder is the circumference, which is 2 pi r. So that's the circumference, and then times the height. And so that is the surface area of a cylinder, and that's where our volume formula for shell method is generated. And that's what we're doing. So actually, before I do the calculus component, I'm going to show you guys another video so you can kind of get a better idea than my lame drawing. So that started quicker than I was ready, but that's okay. So if we were to take each of those little pieces, so it just started spinning really quick, and there's our cylinders being nested together each time. And when they are nested together, they create that volume. And so if we had infinitely many of those cylinders, then we get that smoother edge. And then as it spins around the y-axis, it's creating basically a bundt cake. That's what that kind of looked like to me. So there, starting over. Okay, so back to the beginning. So there's our area, and there's some representative rectangles or segments, and if I were to take just one of them and spin it around, that's creating the outer layer or very thin cylinder, and then from there another one will spin around. So this is just going to halfway revolve just so that you can see each piece. So that's what we're doing. Kind of cool. I think it's kind of cool. All right, so I have errors. Let me go back. Here we go. Okay, so back to where we were. Okay, so there we go. So here is our volume formula that we're going to use. So volume, this is via shell method. Let me write that. So 2 pi, that's our scalar. I'm going to start it on the outside of the integral. But usually when I write it actually out, I'll put it in because I tend to forget. It's the 2 pi. I forget to multiply it in for whatever reason. So 2 pi, and then we're going from A to B. And then our radius. So our radius from the axis of revolution, right? Every radius is from the axis of revolution. So R of x. And then times the height of each of the cylinders, so also h of x, and then with respect to x. And that could be in terms of x or y. So this could be with respect to x, or it could be with respect to y. But in this particular case, so we're dropping to the x-axis, so that's why it's with respect to x. Okay, so we're going to actually do an example at the same time that we're learning this. Okay, so let's do, so find the volume. Okay, so find the volume bounded by y equals root of x equals 4, and y equals 0. So these are our 3 boundaries. And then we're revolving it about the line x equals -2. Okay, so we're going to graph it. So I'm going to go ahead and get the calculator out here. And we're going to just type each of those in. Okay, so y equals, clear those out. Okay, so we have root x. And y equals 0 is just the x-axis, so I don't need to necessarily graph that. I can, but I don't need to, so I'm going to graph it. Okay, so there's my square root graph, and then I know y equals 0 is the x-axis, and then I'm going to 4, so 1, 2, 3, 4. There's x equals 4 here, and then I'm spinning it around the line x equals -2, which is not part of my actual graph. Okay, so let's go ahead and do that. Okay, there we go. Okay, so y equals the square root of x. I have that graphed. And then x equals 4 and y equals 0. So those are the 3 equations, and they're bounding that shaded region. And then I'm spinning it around x equals -2. So one thing that you notice is that we have a vertical axis of revolution. And one of the little tips that we're going to learn is that we have a vertical axis of revolution. It's easier to do shell method because then we don't have to write it in terms of x or in terms of y. And then if we have a horizontal axis of revolution, it's easier to use disk method or washer method because then we don't have to change it. We can keep it in terms of x instead of y. And so that's just a strategy. It's not, it has to be this way. It just is easier if we do it that way. Or at least, you know, for the most of us. So always our first step here is we're going to sketch shade the bounded area. And then indicate our axis of revolution. So we're just going to label the AOR, and we can label it just with putting a spin on it. So that is our first step. So we're going to sketch, shade the bounded area, label our AOR. And then for shell method, we're going to draw in our radius, but we also have to draw in our height. So we need both a radius and we need a height. And that is different than disc and washer. Like all we ever drew was the radius for that. So the first one we're going to do is we're going to draw in our height. So we're going to draw the height in. And that goes across the shaded area. Let me skip this up so you guys can see that. There we go. Okay, so there we go. Okay, so it extends all the way across the shaded area. So I'm going to switch colors here so we can see this better. So the height is the height of the shaded area. So it doesn't have much to do with the axis of revolution, like it isn't like the radius where it has to be drawn from the axis of revolution. So this is my H. Okay. And so now from here we have to draw our radius. And so the radius is a little bit different. It still starts or generates from the axis of revolution. And it goes from the AOR to your random height. So you can't think that that's the only height. It can go anywhere. So from the AOR to your height, like the height you drew. Okay. So from here, so I have to draw a radius from my axis of revolution to my height. And it doesn't matter where I draw it because the radius is the same. So I'm going to randomly pick a spot here, go to a spot on the H, and that is my radius. Okay. So again, if you drew your height over here, that's fine, right? It doesn't matter where you draw your height as long as it's in the shaded. And then your radius is going to be run from your AOR to where you drew your height. And I could have drawn it up higher, I could have drawn it down longer, because it doesn't matter. That radius is going to be the same because it's a cylinder. That's one of the things about the cylinder, is that it would not be a cylinder if it went like this, right? That's not a cylinder. Cylinders go straight up and down, okay? Where they have the same radius no matter where you draw it. And so that's why it doesn't matter where I have that radius. And then once we do that, now we just have to find our h of x and our r of x, and then plug it into our formula. Okay, so now find r of x and h of x. And just exactly like we did before, we're going to do top minus bottom, or in this case for a radius, right minus left. Because it's always a distance, we're always subtracting two things. So look to see where are the endpoints resting. Are they resting on -2? Where are they resting? And so we're going to do the h first. So I'm going to do h of x, or just h. And so I look to see, okay, where is this dot resting?